Hello and welcome back to the lab. Today on the bench we have the 577. No, this is not another 577 repair video. That rabbit hole ended up a little bit deeper than even I was expecting, and I did end up with quite a few of these things. Some stuff happened. This is the 577 that we repaired in a previous video. So he is actually all good to go. Everything's working. But I had some requests to talk about the curve tracers and take a look at them and show some usage. Incredibly useful device. I wish my college, when I was going through college, had one of these. It would have made understanding some of this stuff so much easier. But so in this video, what my plans are is I have tunnel diodes got delivered from Russia. I've cut one out, but I haven't tested it yet, so we'll see what's going on. But, so we may even be able to get yet another 284 fixed. We'll see. I don't know if these tunnel diodes will be able to work in there, but if the tunnel diodes are good, which we'll confirm with the curve tracer, we'll see if we can't get the last 284 fixed. I'll also hook a variety of 2-terminal devices and 3-terminal devices up to the curve tracer, and we'll just take a look at it and see how useful they can be in the lab. This particular curve tracer has been modified. There is an interlock on here. I specifically did not show how to bypass that interlock. If you don't know how to bypass that interlock, don't do it. That removes all the safeties from the curve tracer, and between the collector and emitter pins on both sides of the test fixture, it can put 1600 volts between those two pins at an output of 100 watts. So you can get 1600 volts at 100 watts at the test fixture. In its normal use, this is a hazardous device to use if you're not careful. You do need to understand what you're doing, and you do need to take care with this, especially with transistor cases and things like that. With power transistors, the collector's actually on the case. So even when we're using the test fixture, the whole metal case of the transistor is at whatever the collector's set to. So for right now, because I need to test this tunnel diode, actually I have a test fixture that'll test the tunnel diode because it's got legs. These are standard 4mm banana jacks. If you need to make a custom test fixture for yourself, if you look up the 177 manual, there's a drill pattern for these holes. It's in the 177 manual, not the 577. I don't know why they considered both of these two separate units, but they did. Actually, I'll go get it. This hasn't been shown on the channel before. This is the other socket that can go in a... So there's, on the curve tracers, a little bit of history. There's two, for the 577, there's two, this is kind of called the front porch. There's two things that can go in the front porch. There's a 177, which is the standard test fixture, which pretty much everything has. And then there's the 178, which is designed for actually op amps and other things. This 178's in incredibly good shape. What I'm looking for is I need a couple more of these test cards. These come out the front. Yeah. Yeah. I say they're supposed to come out the front. There it goes. So these come out the front. And there's even some circuitry in the test card for wiring everything up. I'd like to get the test card that has the switch in here, because it'll let you test 4 op amps in one test card. But I also need to get some test fixtures for this. One of the reasons I haven't shown this in the channel before is because I don't have all the pieces. There's a socket that goes here to test the devices. I did find today that somebody makes an adapter for these, so I may order some so we can get this on the channel and take a look at it. I haven't even hooked this up to the curve tracer yet, so I don't know exactly what it's going to do. But that's the 178, the linear test fixture. The other test fixture is for the 576. That's the high current test fixture for power transistors. If I remember correctly, that one actually tests into the kilowatts of power. It's pulsed power, but I'd like to get one of those too. I have some feelers out for those, but I don't have any yet because I'd like to. I have two 576s in the lab as we've rebuilt for the channel already. Those are in previous videos. I'd like to get the high current test fixture for one of them for testing power silicon. I have a small plastic tub with test fixtures. One thing to note is the 300 series test fixtures, the older style 570 test fixtures, some of them, 300 series test fixtures, and the 500 series test fixtures, the 570, 577, 576, and the 370, 371, 372 all share the same test pattern. So the main test is emitter, base, and collector, which would be just this way. These other two pins are collector sense and emitter sense. They're just 4-wire measurement for the test fixture itself. This is one of the older style. You do have to be careful. I have to fix this one. This was a new old stock test fixture. As soon as I inserted it and pulled it out once, it cracked in half. Wasn't anything anybody did, just the plastic gave way. So you do have to be kind of careful with these because they can be a little bit flimsy. I've had to glue a couple on. This is the power silicon test fixture. So emitter, base, and then collector. So if I had this in the tester and I crank this up to 1600 volts, this entire case of this power transistor is at 1600 volts. So you set your hand on this, you can get buzzed. So that's why they usually have a enclosure that goes over top of this. It locks in here, here, and here, and there's a safety switch right here that keeps hands away when there's dangerous voltages. I don't know why, but when people sell these things, they tend to sell that cover separately. Also, that's the first thing that tends to go, get lost. That does tend to happen. They also have double wide test fixtures, which can do grouped components. So, like this can do a dual JFET package or a dual transistor package. You can also do right and left. The fourth pin is the yellow pin, so it's whatever you want to connect it to. With this bar, you can move the bar and connect the yellow dot to wherever it needs to be for the given device. They do make a axial leaded 2-device fixture. I have 2 of these somewhere. I have to find where the other one went. I think the other one fell down behind my shelf. These are from the 300 series. When these show up, they're not cheap. They're way more than they should be for what they are. But they're good up to 2000 volts, so they're fine. And they do 4-wire measurement. Most of the stuff does 4-wire measurement. These are the ones that came. These are the 2-leaded packages for diodes. There's the number, if anybody's curious. These do 4-wire measurement as well. It's a good idea to get 2 of everything if you have one of these, because you can compare devices by flipping right and left. You put 2 devices in and you can compare them really quickly to each other. Going through this, it looks like I have 2 of everything except the long leaded, this guy, because I've only seen him once. But then I only have 1 of the TO66. So they have TO66 for smaller power transistors. They have TO3 for larger power transistors. And then with the drill guide, you can make custom fixtures for whatever you need. These dual packages are nice. I tend to leave one of these on my 576 and it kind of sits there. Usually I leave that one on here too, so, but we will make that safe. So, okay, one side is marked with green, so I'm going to assume that green is positive. So I'm going to set that to the collector, and we'll put the tunnel diode in the test fixture, just like so. So there's the TD, green pins, collector, emitter. So because I have it in sweeping plus, we have plus and minus. You can reverse that with this knob right here, because you can go DC, which is not a sweeping plus, it's true DC. I'll show that later. Sweeping plus, AC, sweeping minus, which flips the polarity, so collector's negative in regards to the emitter. Great for PNP devices, as noted. And then you have negative DC plus. Now that will also invert the display, but that's what the invert switch is for, to bring it back to the corner. So measurements are where you're used to it, because when you say minus over here, the dot will move from this corner up to this corner, and then the graphs will come down and across, as opposed to up and across when it's in positive. So if you hit the display invert button right here, when it's in minus, it'll bring the dot back down here to the corner. So it's what you're used to, I guess. So for the first measurement, given that that's how the, and general controls are collector voltage, 6.5, 25, 100, 400, 1600. That's the maximum collector voltage based on the variable control. So with it right here, all the way up, we'll only put 6.5 volts between the collector and the emitter. Over here, all the way up is 1600 volts. So it's infinitely variable between 0 and 1600. Pulling this out and rotating this knob like so puts in a different series resistor. That's a current limit into the curve tracer. So it will only allow a maximum of whatever the wattage is listed there. It'll self-current limit, which is good when you're testing devices and you're not sure how hard you want to push them. You can set a low self-limit, and it'll you can, when it is in current limit, you can keep cranking this up, but it won't go any higher on the display. It'll just kind of stop. I'll show that a little bit later with some LEDs. So for 2-terminal devices, this isn't used. This is the step offset amplitude. You have 2 sections. You have current and voltage. So you have voltage steps you can apply to the base of a 3-terminal device, and you have current steps you can apply all the way down to 50 nanoamps is the lowest, but then there's also a times 0.1, so you can go even lower than that. So you can generate very small steps. This control is the number of steps. So as you crank this up, it will vary from 1 to 10. The 576 has a actual number. This is just however many lines you have. That's how many controls you have. You can invert the steps, then the offset multiplier if you want to move the display around. 0 is where I commonly keep it, but you can also, if you're going to check transistors at an operating point, you can do opposing amplitude or aiding amplitude. Aiding will add, opposing will subtract. So you could set this to 10 microamp steps with an opposing of 1, which would actually be 9 microamp steps at that point. So each step that it goes up will add 10. When it's on 0, will add 10 microamps to the base. So it'll give you a sweep of what the device does under actual operating conditions. It's really, really great for testing leaky transistors. Having one of these in the lab was vitally important when I was repairing the 5200A. because one of the power transistors was leaky. It had been damaged when the negative 190 volt rail let out the magic smoke. So that was yet another video on the channel. Actually, that was an early video. Positioning controls, horizontal and vertical. Pushing these out is a zoom function, multiplies by 10. Fine is the smaller knob. Larger is the coarse knob. One of my 577s is a very early unit. It didn't actually have this dual pot setup. I like the dual pot setup a lot better. When you're at a times 10 multiplier and you're actually trying to line up the graticule and take measurements, only having one pot, the control gets really, really touchy. This is just sweep rate, slow, fat, normal, and fast. Whether you want a repeated step family or a single step family, pulsed step rates. Vertical is current per division. You can go from 2 amps per division all the way down to 2 nanoamps per division. And then you can actually multiply that by 10. So at its lowest setting, it is 200 picoamps per division. Obviously, it's an analog device. It gets noisy down there. But for late 70s, 200 picoamps per division times 10 is 2 nanoamps full scale. That's pretty impressive. That's enough rambling about the controls on this thing. Let's start testing some components and see what we can do. One other thing to note on these curve tracers is to save the tube on the 577. This doesn't happen on the 576. That's one of the reasons why the 576 tubes are tired. There's a dimmer function. So if I turn up the intensity, I have the variable control all the way down. If I turn this up, see how the spot gets a lot brighter? So what happens is when you have the spot at a comfortable viewing level, if I turn this off, the spot actually extinguishes so you don't burn in the tube. Really, really nice feature with the 577s. I like it. I like that a lot. So what I'm going to do is we're going to center that right on the corner. And I'm going to zoom out a bit, bring this down, and I'm going to leave the camera so you guys can actually see all the controls. I'm not going to zoom in on the screen on this one so you guys can see what I'm doing when I'm manipulating the 577. So we have our tunnel diode. I don't know what the polarity is on these because I've never used Russian TDs before. So I'm assuming green is plus because it's marked, but we're about to find out. The one thing I'm going to do is I'm going to turn this up slowly, and I'm going to look for the curve. If I see that curve start, I'll know I'm on the right polarity. Because if you have a tunnel diode in backwards, they're just a resistor. It'll be a straight line, which I'll show in a little bit. So let's see. There's 5 milliamps. So at 5 milliamps, we're running about, let's see, what's my vertical scale? Vertical scale is 0.1, 100 millivolts per division, so that's about 20 millivolts and 20 milliamp. There's 10, or no, that's 5 milliamps, sorry. That's 20 millivolts, 5 milliamps, so there's 10 milliamps. Okay, I'm starting to see a slight bow to the trace. I don't know if you guys can see it on camera, but the trace is starting to have this slight curve, so I think we have the polarity right. So let's keep turning it up. So that's 15. There. Now the bow should be pretty exaggerated because we went into the next. There's 20. Okay, so I will zoom in on that just so you guys can see what I'm seeing. So you see how it has that kind of curve to it? The line isn't straight. That means the tunnel diode is starting to forward bias, so we should hit IP very shortly. So I won't adjust anything on the curve tracer except this. And there it goes. It's way over here. So let me adjust the horizontal volts per division. This is going to be 200 millivolts per division. We'll turn this up. And there we go. So that is a functioning tunnel diode in the correct polarity. Everything is good to go. And we're right around 20 milliamps. So this has a huge jump. I'm going to be kind of interested to see what this does in a 284. Given that we have a bias adjusting pot, I'm going to rebuild the airline, and we'll throw one of these in a 284 and see what kind of square waves it gives us. That should be interesting. Okay, so just like that, we confirmed that this TD is good, and it'll probably work. We know what the IP is. The IP's running a little over 20 milliamps, so perfectly in line for a Type 284. So awesome. Here's my random box of silicon parts. So we got a bunch of stuff we can test, actually. Here's a couple of these white LEDs we've been messing with. Burn up a couple of LEDs. We will not be nice to them. Let's set this for 10 milliamps of division. No. We'll set this for 200 milliamps of division. That'll work. That is down here. I need to go the right way. 200 milliamps per division, because that's amps. Depending on what version you have, the 177, the scales are actually different. So it can sometimes make it interesting. Okay, we'll set this to right. Here we go. I gotta change this because my volts is low. Alright, so there's the current limit. So what you guys saw is I'm at 6 volts. I'll hit V forward. So I'll crank this all the way up. Because I'm at a low current limit, it's self-limiting the curve tracer. This is all the way up. I could even kick this to 25 volts, turn it all the way up, and it's not going to do anything because it's limiting the power into the device. So good way to protect the device. This unit is fully capable of burning up devices, which we're about to do. So I need some more current. I'll do 100 watts. So what we'll do is, there's our V forward. So there is 100, there is 200 milliamps into that LED. So it is very bright. And there it goes. It's starting to die already. See how it kind of drops? And see the blue shift in the LED? That means the LED is getting overheated. All right, let me bump up the voltage a little bit, get some more power. There's 100. They're right there. There's the blue shift, and the diode died. So this can actually tell you if there's a failing component. We'll kill one more. So while I turn this up, watch, I will turn it up slowly. Watch the trace. It will actually show you as comes on. There's 200 milliamps. Actually, let's exaggerate this more. All right, there's 50 milliamps of division right there. So that's 51, 52, 50, right there. It's already starting to get stressed, how it pulled down. So we'll bring it back down. Right there, how the trace is bouncing and moving. See how the trace is not standing still? what we're actually seeing, I'll give it a little bit more power. What we're actually seeing is the diode slowly dying. So this is stressing the components so much. Oh yeah, that's warm. That's real warm. It won't live long here, but you'll see it slowly. We give it a bit more power. I want to get this right on the verge where it's kind of fighting. But as the trace falls and it moves further this way, it means the voltage across the device is going up. So the resistance is going up, which means there's a higher voltage drop, which is causing the current to go down. That is a very, very warm diode. There it goes. There it goes. So with the beam opening, that's showing capacitance now. So this is a very stressed and unhappy LED. So we're seeing the LED at an incredible stress level here. The light output's now pretty low. It's not very bright anymore, but it's very blue. This LED is actually taking quite a bit. There it goes. Boom, done. LED's off. So current went high, overheated, but now it has, we're at 2, 4, 6, 8, 10 volts across it. So that LED had 10 volts, it was dropping 10 volts. So you do have to be careful with curve tracers because these can burn stuff up. Okay, I have put a 2N3055 in the test fixture. This is a much beefier component, so we're gonna kick it up to 100 volts. When we turn on 100 volts, we have a red light that says we are now entering the danger zone. I have to be careful because there could be upwards of 100 volts on here. Let's see, we want 10 volts collector because we're going to get up around 60 volts because the collector voltage is right around 60 volts. Bring it down to 9 watts. It says 15 continuous. I'm assuming that's 15 amps because this is a power transistor, but we'll see. And then let's do, yeah, 10 microamp steps on the base. Shouldn't be bad. All right. We'll move up, and we'll adjust it from here. Okay, we have absolutely no gain. So there's some gain. Now we have 10 volts, 20, 30, 40, 50, 60 volts. All right, see how it starts to curl here? So it's straight. These lines are straight. Everything looks good. So 60, and there it goes. Starts to break down. So curve tracer can also show you breakdown voltages of the silicon. Now that didn't damage the silicon at all. It just told us because we didn't overheat it. But so it will get to 60 volts, but not with a decent base current. Because that's 60 volts right there, but we're already starting to break down up at the top. So the device is kind of lackluster. It's meeting spec-ish, but I wouldn't use it at 60 volts. I'd use something bigger. Let's see. We can change the sweep rate to fast. It'll wiggle a little more. Go slow. be a little slower. Let's see. If you do single, you get 1 pulse. And then you could do pulsed and get the dots. So you actually read here where the dots are for the pulsed. You don't have the lines. And we can go all the way up to 10 traces. We'll do normal. Won't do pulsed. We'll do swept. And there's 10 traces. And you can see at the high base current, because every trace that you see is another 10 microamps of base current. So if I expand these more and bring these down. So 0 base current, 10 microamps, 20, 30, 40, 50, 60, 70 microamps of base current. So now if I had 2 transistors, what I could do is with the same settings, I could flip back and forth between them. And depending on how the scale changed, it would tell me how closely matched the transistors were. That becomes important at like push-pull amplifiers, things like that. Some hand grading of parts. I could also go through all those tunnel diodes and find out which one is the closest right at 20 milliamps, but I don't think that's going to matter. Always turn this down before you put your fingers over here and make sure that lights out. Okay. For this part, we're going to actually flip this to AC. And that being said, we're going to make sure our dot is centered, which it is. And I need to come up in voltage. We'll come down in current. Kick this over. And I just need it to be sensitive. I don't need it to really do too much. Let's go to 20 collector volts. So that's 20. 40. Oh. Interesting. Okay, but let's measure it. So what we can do is let's go back down to 10. And since we're coming this way, and we need, because if I spin this up, we're off the scale, so we can't read, can't measure. So if I need a little bit, I need more this way. So now with it set to AC, it's a sweeping voltage, positive and negative. So if I spin this up, there's our turn on. So we're at 10 volts per division collector, so that's 10, 20, 30, 40, 50, 2, there we go. 54 volts. Well, these are 6 volt, 56 volt, but this one's going at 54. But 56 volt Zener diodes, 5 watts. Let's see what happens with a coil. I'm going to put a light amount of AC in here. I honestly don't know what's going to happen. I've never actually curve traced out a coil. So not much happens at these frequencies. This coil is a dead short. So I was hoping for a little more than that. Well, I got the coil out, and using my LCR meter, the coil's kind of beefy, actually. It's 43.7 microhenries. That's a giant coil. Q factor looks okay, too. Yeah, so at 60 hertz, it doesn't do much. But at 1 kilohertz, it's a 43.7 microhenry coil. Okay, one other part to hook up to the curve tracer. We have a ceramic dog bone capacitor. It looks like an open, but let's give it some zoom. And there we go. That's what a capacitor should look like. Now that's sitting at 0.5, so 500 nanoamps per division. We have about 1 division of separation. Now this is also frequency dependent because this is a 60 hertz device. It's based on line power, so the reactance of the devices is going to be low because of the frequency is super low. But let's hook that up to the LCR meter. 15 puff. So a very, very small capacitor, but not bad. Here's a bigger cap. So let's see how this one looks. This is also an extremely high quality capacitor too, so but we're going to take it pretty high. Oh wait. Yeah, that's right. So that's 100, 200, 300, 400 volts. So that's a 400 volt 22 nanofarad capacitor. It's doing a lot more with the capacitance. That's at 2 milliamps per division. A perfect circle is what you would expect. This is not an optimum test setup, for sure. Let's give it a real challenge. I actually don't have anything in my lab that'll measure this resistor. Let's see if the curve tracer can do it. Yeah, we'll leave it. We'll leave it on AC. If it is measuring the resistor, we should get a diagonal line as the sweep goes positive and negative. Let's see what happens. There is so much capacitance in the circuit. This is what the looping compensation does, because we are measuring a very, very stout resistance. Okay. That's 100 volts per division. So, oh, what are we even measuring that at? So that is measuring, let's go down one more. Okay, we don't need 1600 volts for this, so let me turn it down to 4. All right, so that's 50. There we go. So now, let's see if we can't line this up a touch better. Oh, that doesn't look too bad. So there's our resistance that we're measuring. Now, this is really incredible actually, and this right here is why I needed to fix that looping compensation control on my other unit, because you use the looping compensation control to bring this together as smooth a line as possible. So we're at 10 volts collector per division. So that's 10, 20. Actually, I'm going to measure it here. So 10, 20, 30, 40. So 40 volts. And we're coming in almost dead on that corner at 2 nanoamps. So this is 2, 4, 6 nanoamps. So at 10 volts, this resistor is passing 6 nanoamps of current. Let's see what the math works out to be. So the way the math works out is it's 6.33333 times e to the minus 9. So that's with 38 volts at 6 nanoamps. So here's the crazy part. These are 5 gig ohm resistors. Okay, I had to fiddle with the controls a little bit to get the voltage and everything correctly. However, I did get the numbers to work out within the tolerances of the unit. So, with the optimum readout, we have 26, just over 26 volts, because I had to back it down to 25, so it's just 25, just over. And we're at 5 nanoamps per division, so it's 26 volts, 5 nanoamps. And if we do the math out, 26 divided by 0.000 milli, 000 micro, 005 nano, 5.2 times 10 to the minus 10 to the 9th ohms, and the unit has a 3% tolerance, which allows me 166 megohms of plus minus 166 for a 5 gig ohm resistor at 5 nanoamps of current. Now we're slightly off the scale-wise, so slightly off the calibrated portion, but yeah, pushing the unit to its absolute limits, we can get it close enough. And that was assuming that the resistor was perfect, because these are 1% resistors. And at 5 gig ohms, 1% is another 50 meg. So if I take 166.67 plus 50, puts me at 216, which actually, if we take into account and we assume the tolerance of the resistor plus the tolerance of the unit, we're actually in spec for measuring a 5 gig ohm resistor on a curve tracer, which is, I made a lot of assumptions there. I know I made a lot of assumptions there, but 5,000 megohms, which was pretty impressive. Thanks for stopping by the lab today. Hopefully this video was informative on sticking random things on a curve tracer. If you guys have any other questions, or you want to see me put more things on a curve tracer, definitely let me know, and we will see what we can make happen. If you guys have any suggestions for videos, also let me know, and we'll see what we can make happen. I am always looking for suggestions from you guys. You guys are the reason the channel exists, so I want to help out where I can. I'm going to get the, I'm going to put this tunnel diode in another, in a 284. If you guys are interested in seeing that video, let me know. That'll be the third 284 video. I don't want to turn this into repairing 284s. But if you guys want to see it, let me know. I'll definitely share the results of the assembly. I just don't know if you guys want to see another 284 repair video, although that one's in rough shape. So, all right, bye for now. I'll see you guys in the next video.